Today, I'm going to be talking about my research in biomarker development in motor neuron disease, specifically looking at how Tensor EIM of the tongue is able to identify the impedance signature of disease progression. So firstly, just a bit of background on motor neuron disease, which is often referred to as amyotrophic lateral sclerosis, or ALS. It's a progressive neurodegenerative disease which is characterised by the degeneration of both the upper motor neurons in the brain and the lower motor neurons which are in the spinal cord and extend to the muscle fibres. The disease is relentlessly progressive, with median life expectancy reported as less than a year from initial diagnosis, and we currently have a limited number of effective biomarkers for measuring the progression of ALS. So at the moment we are primarily limited to a symptom questionnaire, which is the ALS functional rating scale, and then also muscle strength measurements, but both of these are highly subjective and lack sensitivity. There's currently no cure for ALS, so the development of a more objective and sensitive biomarker of the disease is crucial for use in clinical trials, and these are highly important in order to progress the effectiveness of patient care, to prolong survival, and in developing potential curative treatments for the disease. So a new candidate for a biomarker that I've been looking at in my PhD is called electrical impedance myography, or EIM. So electrical impedance is just an electrical property of any material, and it represents the total opposition presented to a passing AC current. It's a complex quantity with real part resistance and imaginary part reactance, and equivalently can be written in polar form in terms of the impedance magnitude and the phase. It's a fairly simple quantity to calculate, just calculated as the ratio of voltage to current. So then the process of EIM just involves taking these impedance measurements of the diseased muscle over a number of different frequencies of AC current. This then outputs a spectrum of values as shown in these example plots here of the impedance magnitude against frequency and the impedance phase against frequency. So the dataset that I have been analysing was collected in the tongue using this impedance device that was developed by our team here in Sheffield, and this specifically assesses bulbar ALS disease, which affects the muscles of speech and swallowing. So measurements were recorded in 30 healthy volunteers who were seen at an initial baseline visit and a 6-month follow-up, as well as 40 ALS patients who were seen at baseline 3 months, 6 months, 9 months, and up to 12 months. The device uses 14 frequencies, starting at 76 Hz, going all the way up to 625 kHz, and measurements were taken both for a central placement in the midline of the tongue and a lateral placement at the tongue edge, and then also for 3 different electrode configurations, which explore measuring 3 different directions through the muscle, and these are defined by a pair of electrodes that are used for the current injection and a pair used for the voltage readout. So the 3 configurations we used are shown here in this diagram. So overall, this is a very high dimensional data set. We have measurements from our 70 participants over a number of different time points. Then we have the 3 different electrode configurations, the 2 device placements, central and lateral placement, then 14 different frequencies, and then we get out a complex output. So each impedance has 2 values, one for resistance and one for reactance. So overall, this gives us 3 times 2 times 14 times 2, which is 168 data points per participant visit. So in total, I'm working with over 20,000 data points. And so the high dimensional nature of this led me to explore different dimensionality reduction techniques. So I came up with a dimensionality reduction method, which I refer to as Tensor EIM. And this involves using a technique called non-negative tensor factorization, which computes a part-based representation of high-dimensional data. So the high-dimensional data set is built up into a 3D tensor with one dimension of size 28, which is the 14 spectral resistances and reactances, and then the next dimension is of size 6, which is the different measurement types made up of the placements and the configurations. And then the final dimension is each individual participant at every time point. And then the non-negative tensor factorization procedure decomposes the multidimensional tensor into a sum of rank 1 tensors. So then the rank of our decomposition is something that needs to be chosen. And so using a rank selection criteria algorithm, I ended up selecting a rank of 3 for the decomposition. So basically what this does is reduces the output down from 168 data points per participant to now just having 3 outputs. So doing this procedure, we identify 3 common spectral modes, A1, A2 and A3, which are shown here in their magnitude and phase spectra. And each of these will contribute to differing levels in all the measurement sets within the dataset. So then each participant will receive a corresponding weighting for how much each mode contributes in their recording. So these are C1, C2 and C3. And then a combined Tensor EIM score is calculated as the first principal component, PC1, of these 3 weightings. So this further reduces the dimension down to just one single metric. So moving on to the results that I found when applying this Tensor EIM method. So firstly, in order to assess the general group trend of change over time, I actually introduced the visit as a dimension in the decomposition and found that when looking at a 6-month period, the healthy controls are stable, as we would expect, while the patients represent a general shift to the right in the phase impedance pattern. This can be understood as an increase in the centre frequency, which is the frequency that characterises the phase minima. So then the next assessment I made was looking at how our NTF outputs and the Tensor EIM score correlate with an overall symptom score. So this symptom score just combines all the information we have about the patient's disease into a single score out of 36, where a lower score represents more severe disease. So using a Spearman correlation analysis, I found significant correlations for each of the individual NTF metrics, and then the best correlation for our combined Tensor EIM with a Spearman rank of minus 0.7. We can then compare this to just looking at a single frequency value from our raw data set. So on average, just using a single value does not give any significant correlation with the symptoms, and even running an exhaustive search to find the best single frequency with an FDR correction applied does not perform as well as our combined Tensor EIM metric. So then to assess the effectiveness of Tensor EIM to sensitively measure disease changes over time, I applied a linear mixed model to the change over time in both the patient group and also our healthy control group. And I repeated this for the tongue strength, the ALS functional rating scale, and also a single frequency EIM assessment. So the p-values of significance of change were calculated at each time point, and actually neither the tongue strength nor the single frequency assessment find any significant change. The ALS-FRS reports 5% significance by 6 months and 9 months. However, the Tensor EIM finds 1% significant change by 3 months and then 0.1% significant change at 6 and 9 months. Finally, to further demonstrate the superior performance of the Tensor EIM, I made an estimation for clinical sample size when using each different biomarker. So this was done using this equation, where the distribution of the slope of change in each parameter is used, and I calculate this at 1% significance for 90% power. So these sample size calculations clearly indicate that Tensor EIM seems to be the most effective. We find that 3 times more patients are needed in a clinical trial using the ALS-FRS, and over 4 times more are needed in a clinical trial using just a single frequency EIM assessment rather than looking at our full high dimensional data set and reducing it down through our Tensor EIM method. So in summary, I have developed the Tensor EIM method, which captures our information out of the very high dimensional data set into a single objective measure of disease. This is able to sensitively capture disease changes much more sensitively than the single frequency EIM, tongue strength, and the ALS-FRS. This method of dimensionality reduction has many advantages over just applying exhaustive feature selection searches, such as the wrapper method. So these include a reduced chance of overfitting to our dataset, since NTF is an unsupervised technique, and also the ability to deal with missing data points and being significantly less computationally expensive. So overall, more work is needed in exploring the direction of EIM changes on an individual level. Some patients see more sporadic changes which can change direction through the course of their disease, and further work may help us understand what this can tell us about the disease process. On the whole, Tensor EIM shows a lot of promise as an effective biomarker in ALS and could significantly improve clinical trial design.